Okay, so so this is a project. This is my first time I've ever built a fourth, so kind of a newbie, but I got some very good people working with me. Dimitri out in the UK is a systems verilog expert. He does ASIC chip verification over there. He's in the verification department. Dr. Ting is also on the team, and Chao Cheng is also on the team. So the idea is we're building in a fourth engine in an FPGA, which many people have done that, but we're using a different approach. The different approach is there's a difference between behavioral verilog, which is very C-like syntax, and RTL, which is register transfer logic. So if you look at Dr. Ting's VHDL version, you look at the J1, there's at least a half a dozen fourth engines already out there. They're done in RTL. The problem with doing everything in RTL is you're changing bits and registers, and you're doing everything at a low level. It's almost like programming in assembler. System verilog behavioral looks very much like C, like it supports type def, it supports enum, it supports very high level code, and when you don't have a lot of modules that you have to hook together. So one of the problems with RTL is you create a module for the arithmetic unit, and then you have to define its IO, and then your main processor, executor needs to map to that. So now you have to, in that source code file, you have to create this map between the two. It's kind of cumbersome. Whereas our code actually resides at the moment in one single file. Excuse me, I'm just getting over a little Omicron. So what we want to do is we want to build a fourth engine that you can use parameters, which are like pound defines in C, and you can change the size of it, 32 bits, 16 bits, 64 bits. We're standardizing on 32 bits at the moment. We want to build this module so it can be actually a full computer where even the outer interpreter is written in system verilog. Okay, so a lot of times you create a fourth engine, and then you write some of the remainder of the fourth in fourth, right? But we're doing everything right up to the outer interpreter in system verilog. So I call it kind of a supercomputer on a chip. So obviously fourth is a virtual machine, and the amazing thing that makes fourth stand out from every other quote unquote language on the planet is it's a virtual machine. It's not just a language. It's actually a blueprint on how to build a microprocessor in silicon, which Chuck has built quite a few of them. So he has an NC 4000, the Shaboom, the RTX 2000. Now the RTX 2000 was used a lot in space. It was promoted by Harris Semiconductor. Then we have the Green Erase 144 multi-computer chip, and there's a lot of the world of for silicon. There's a lot of an Ultra Technology website. You can go look at some of those. The reason we call it the Core 1 is it's CISC over RISC engine. What do we mean by that is the RISC engine is fourth, so a fourth engine. But on top of that, we want to extend fourth to use more higher level and AI constructs. So, for example, Dimitri has written Prolog in fourth, and we we're going to take the Prolog engine, not necessarily support Prolog syntax, and we're going to incorporate that in this new processor. Now, one of the other things about it is when you define your own word, you can make that word an opcode. So the other benefit, the way we're doing it, is there isn't a timing issue where you have to keep the opcodes very primitive because you're trying to meet, an opcode has to finish in 50 nanoseconds, for example. We have a busy flag, and so basically, if your opcode needs more time, it stalls the execution engine until it completes. And this is going to be really important for allowing you to create your own opcodes. You don't have to worry about timing. Yeah, so like I said before, we're using a very high-level behavioral system Verilog code, which is really easy to understand. We're going to look at the code at the end. So the idea is you build the high-level code, let the synthesizer build the circuits. You don't build the circuits. So RTL is very much like you're building the circuit at a very low level. We can also put multiple of these fourth engines on a chip, and so we can build a multiple processor chip, which we'll go into a little bit later. So microcode fourth programs and words can be a boot ROM. So internal to this fourth engine, inside the FPGA, you have local RAM right inside the FPGA. You have local boot ROM right inside the FPGA. Okay, it's limited space, but it's pretty good size for fourth. It's not bad. So you can actually, in the boot ROM, you could define words in fourth using the fourth opcodes, and you could call them. So you could so for example, if you wanted to conserve memory space, or memory and flash and everything else, you might want to consider writing things in fourth, because system Verilog is going to create circuits, whereas the fourth is just going to consume a couple bytes of memory, right? Or 4 bytes. Okay, and like I said before, the core opcodes can be complex, taking many cycles. I think that's a pretty interesting feature. So, and these words will execute at the speed of silicon if they're written in system Verilog. So system Verilog, which is a very high level language, is your assembler, and it's creating hardware circuits. So this is going to run really fast. So we want to steal, borrow high-level concepts from other popular languages. We can grow the computer from 32 bits to 64 to 128, however the future grows in that regard. You just change one parameter word, and you can change the width of the bus. So as the FPGAs get denser, if they're 10 times denser 5 years from now, you can make it wider. So you can network multiple 32-bit fourth engines together over an internal network inside the FPGA. So that's kind of like the green arrays, but they're 18-bit processors with 64 levels of RAM, and that's very limited. Whereas you can put as many of these things inside the FPGA that'll fit, and you can assign however much RAM you want, right, for each one. You can store source code in flash or on disk. You can even, like in the boot ROM, you can store source code actually in the boot ROM inside the FPGA. So at work, we're using a RISC-V. We're using an SRAM. This is the way it's implemented at work. The RISC-V takes 10,000 LUTs. Now, LUT is a logic unit that we use in FPGAs to kind of measure how much logic It's a logic module. So when you pick an FPGA, it might say it supports 10,000 LUTs or 2,000 LUTs or 100,000 LUTs or a million LUTs. The RISC-V consumes 10,000 LUTs. Right now, we have the basic outer interpreter working with a single character word width. So it's not a string yet, but it is working, and it's 2,500 LUTs. So you could fit 4 of our 4th engines in the same amount of fabric space as a RISC-V. So this is our FPGA computer. So we have the internal boot ROM you see in the lower left. We have internal SRAM, the 4th processor. The serial controller is written in System Verilog 2, so it runs really fast. So this thing's going to be able to compile on the fly. It's going to compile extremely fast. You see in the design summary, this is the actual utilization of the $4.50 FPGA that we're using. So we're using about 50% of the chip right now, and it's a very low cost chip. So here's an example of where you're going to use external flash and external RAM and an SD card, for example. So you can have a display controller that's written in System Verilog, serial controller, which we already have written, 4th computer and the boot ROM and the internal RAM. And you can also tie to external memory and SD cards and other peripherals, because this will be an excellent embedded systems engine as well. So here's an example of making where you can have an external display. You can have a keyboard. We can have multiple 4th processors doing different tasks. You have a main 4th processor that is your user IO, that would support the display in the terminal, and you have these other 4th processors, kind of like the green arrays, doing different things, controlling different IO. So here's an example of an embedded system version, and here we have 3 instantiated processors. So that would be about 7,500 LUTs. So you could do this on a $12 to $20 FPGA. You would have an 8-bit network controller, so you could the 4th processors could send character size characters across this at 50 megahertz probably. So it'd be very fast. You see we have a terminal over there on the right side. So you can actually program an FPGA just using a terminal. How can you do that today? Who else does that? Only if you put 4th inside, right? So here's another example of something I was thinking about. So the NV-SRAM, they have a newer RAM technology. They have non-volatile SRAM. So that's an actual chip. I've actually bought the chip. I bought enough parts, physical parts, to make 20 development boards. Hopefully by the end of this year, I'll make that. But I did buy the parts, so kind of committed. But what's interesting is you turn the computer off, turn it on again, and you're right where you left off, because it's non-volatile RAM. I've talked about this a bit, but some of you are new. I designed a robot called the Whiskers intelligent robot back in the 90s. I wanted to build a robot with artificial intelligence where, instead of programming the robot and you figuring out the problems, I wanted to be able to teach the robot, if you're in this situation, do this thing, and have it actually make the decisions. So I created with this architecture I called the Triune architecture. So the Triune, it includes special kind of multitasking, which I'm going to talk about on the next screen. It's going to be easy to implement other languages in this 4th. Like I say, Dimitri already did Prolog. I did a neural network language, which I can port over to it, probability engine. Vision systems and voice recognition, I would do probably get it outside. Vision, I would probably do inside. So the Triune operating system, it emulates the 3 levels of the human brain. It's sometimes called the reptilian brain, but your cerebral cortex, which is your conscious thought, that's your goals and learning level, behaviors and tasks, is the limbic system, which is like controls your automatic breathing, but you can override it, right? Instincts is like you touch something hot, your nervous system pulls your arm away. It sends a message to your brain, pain, and then a behavior kicks in, or you analyze the situation with your goals and learning level. So it emulates the Triune brain, and it makes intelligent robots make decisions in real time. It's very good at that. So this talks about the 3 levels. The multitasker is kind of interesting in this system. So what I did was I used a counter timer, and I do a periodic interrupt. This is how I built this. And it executes, say, 1,000 times a second. And so in the interrupt service routine for that counter timer interrupt, the first thing it does is it reads all the sensors in the robot and updates variables, in the memory space to what the new values of the sensors are. Each flag, there's flags associated with each one of those, and one of them is what motor override would I do if the sensor sees something, like say a left whisker would I want to turn right, or a right whisker I want to turn left. So that's all done automatically. At the end, I also have a counter for about 100 hertz, at 100 hertz rate. It calls a task behavior list. So that's a list of CFAs of words, and it executes them from start to finish. So priority 1 is at the top. So you want to have high priority tasks on the front and a low priority in the back. So the back might be hold compass heading to 360 degrees. So if it sees your behaviors in front of those, might be, I got a double whisker hit, I got 2 sensors in the front see something, and it has some behavior for doing that. Now, when the behavior kicks in, it's cooperative multitasking between the goal level and the behavior. The behavior takes over, stops goal level processing, deals with the situation, and then returns control. And then the goal level continues where it's going. So it's a preemptive multitasking with cooperative, and we're going to build this into this system. It works really well. So here's an example. See a $24 lattice board you can get online. It has 57,000 LUTs. We're at 2,500 LUTs, and we're not that far away from finishing. So I'm estimating we're going to be at about 3,000 LUTs for a single core. So you can buy a $24 board and you can play around with our system. And we will make it'll be open source, open hardware going forward. We're keeping it kind of limited right now, access, until we get something that works. I also, I started on a creative RISC-V board that cost $160. Now, the FPGA on that board is only $20, has 37,000 LUTs. You could put 10 of these, 11 of these chips in there, and these processors, 32-bit processors. I don't know what you'd do with all that. So there's kind of a block diagram of it from the tools. So here's some of the things that are kind of inputs to our thinking after the 4th engine gets built. We want to maybe implement some Prolog or some Lisp type things, expert systems. We want to experiment with different things to make an intelligent computer on top of 4th. So we want to build high-performance, low-cost, intelligent embedded systems, research novel 4th-based computer architectures, research develop AI on top of 4th, add high-level constructs to 4th. Easy way for beginners to learn about FPGAs because they don't have to learn all the tools. They could actually download this thing. They could create some little programs in System Verilog, make them a word, and just call them interactively over the terminal. It'll fit into it. There's actually a $2 FPGA it'll fit in. It has 3,900 LUTs. So it'd be a controller for intelligent machines and robots, and bring new people into Forth. So the micro engine development that works. The Forth outer interpreter, we have the basics working with a single character right now, but it does work. Dimitri, is working on that. So we're probably within the next 30 days or maybe a little longer, we'll have the full string capability working. I did open up a GitHub. I created a Facebook private group that anyone on this call, if you'd like to join us in this group, we're still in the build phase, the development phase. So, you can like ask questions, or you could kind of, if you're interested in it, you could, talk to us about it. But we're pretty much focused with this group and developing it and getting it working right now. Obviously I want the Triune OS multitasking engine implemented, which is going to be extremely easy on an FPGA. Local variables. I really like the idea of local variables that are named. The biggest complaint that anyone has about Forth is the stack. And with all this processing power, if you're going for speed, absolutely, right? Forth programmers, stack, greater than, less than, to dupe, rote, swap, good stuff. But for newbies, if they could use a name instead of that, it would make their programming a lot easier and probably get a lot more people into Forth. So we are going to support that. I want to have string and array extension words because you got to manipulate strings and arrays in modern programming. So this is kind of an example of what my thinking is. I'd love to hear your opinions on it. How I'm thinking about implementing local variables. So there's a word called box. Actually, yeah, the way I wrote it, I shouldn't have a stack picture in there. But anyway, so you call it an int, and then local is an immediate word that will take 12 and then store it into the width variable. That I'm thinking of a string stack or a stack for local variables that has the string name in it, and then also the number at each level. And then when you exit, when you run exit at the semicolon, then the string stack is cleared. But then you could use width value. So value is really fetch, and now is really store. So 5 width store, 5 width now. But it's more the way you talk to someone, right? 5 width now, 6 height now, and then draw rectangle. Because my long-term goal is to make it very human interaction, human readable. Ran across this language, which Kevin has already said he's going to put the link up there. It's very interesting. This guy has been working for almost 10 years now on this thing called Factor, and it's Forth, but he's built a lot of stuff on top of it. He's implemented Smalltalk and Lisp constructs. It's fascinating. I'd love to maybe at the next meeting have everybody watch this thing. It's an hour and a half long. I get it, but go in at least 30 minutes. If it doesn't hook you in 30 minutes, fine. But the first 30 minutes gives you a flavor of what he's doing. I think it's fascinating.
I think that the thing to probably going to do is send everybody the link, incorporate it in the meeting announcement, and say, okay, we're going to talk about this in the last half hour of the meeting. And you're on your own as far as watching it. If you want to participate and watch at least half an hour. But I don't think that putting it in line in the course of the meeting is a good idea, in my opinion.
Yeah, that's fine. I just wanted, it would be great. I would love to hear opinions on it, because I think some of the things that I wanted to do with our embellishing forth, he's done a lot of work in that area. Although to me, it's a little more computerized. Like, he's got a defining word called tuple, and so it's still computerized. I'm kind of going for more English level stuff, but a lot of the stuff he's implemented is really cool. So this page here, if you want to join our Facebook page, there's a link to it. Like I said, we're still building it. I kind of created this page for people that are actually working on it, but if you want to join it and you want to keep, see what we're talking about, I called it AI and robotics for a good reason. I didn't call it the fourth computer project, because long term, after this is built, we're going to be doing a lot of discussion on how to use this in AI and robotics. That's my presentation.
Hi. Boy, one of the things is I definitely have to look at the implementation of Prolog in fourth to really see, well, one, how minimal it is and exactly what it is that it does. Incidentally, I looked at Factor, and I've got a link, I don't know, geez, probably some years ago. Slava Pestov, who I believe is the guy who wrote Factor, actually is definitely one of the world's brilliant programmers. But my feeling about Factor is that it sort of has a kitchen sink of all sorts of concepts in it. It handles genericity of objects that I've not gotten to in fourth. But one of the most fundamental things that I'd say is there's a sense in which I'd rather have 10,000 product computers than anything that has logical depth in it in terms of going and approaching AI. I mean, I really see the parallelism. I mean, I know obviously that's intrinsic in everything I've done, but it's that parallelism. But I definitely have to go and take a look at just exactly what your Prolog and how deep it is, because at your gate level, definitely.
Yeah. There's one thing I almost forgot. I was going to go over the source code, so I better pop in there. I got what, 7 minutes, Kevin? Okay.
Donald, was your email address donaldrgolding@gmail.com? Was that correct?
That is correct.
Thank you.
So I was going to go through
You
the
can have
source
more
code.
than 7 minutes. You can have 12 minutes and 12 seconds.
Wow, you're generous this time. All right. I think you might find the source code very interesting. Can you guys see it pretty well?
Yes, we can.
Okay. So here's the data width of the system, right? So you have to subtract 1 in Verilog, because 31 down to 0 is the way it works. So this is where we parameterize the whole system. How big is the boot ROM, that sort of thing, very high level stuff. This is where we create the opcode. This is an enum for opcodes. So system operators got execute, abort, end boot, run boot. So it's really easy for you to create your own opcodes. Just do a underscore, your name and comma, and now you just created the opcode. You didn't create the processing, but you did create the opcode. So these are all the different opcodes. Let's see. I don't know if I can move this over. Okay. So here's the memory opcodes. Error opcodes. Some of these things, a lot of these opcodes are going to disappear because we're not going to need them. I kind of put all the opcodes down that I thought we might need based on looking at you know, our NZ4th and F83 and that sort of thing. You can also obviously create your own opcodes, like we created IO LED, IO button, IO fetch, and IO store. That's storing and fetching things off of you know, parallel pins on the FPGA, for example. So here, logic is immediate. So we're creating the opcode as like a type. So you can have immediate flag built into the binary, the bit pattern of the opcode. So we can test the highest bit flag and see if the opcode is immediate or not. Should we compile it? If we're in the compiling state, which I'd like to talk to you guys about state and compiling, then immediate, if the bit is set, it'll execute it instead of compile it. There's some people have been talking about, I've been reading about stateless fourth, like color fourth, and I'd love to hear your guys' input on that. So here we're defining some of the addresses, true and false, instead of, you know, using the bit thing. These are different inputs and outputs are defined right here. Okay, so we have, this is a memory pointer. This is the, right now we have a separate memory pointer and a boot ROM pointer. We could make them the same, and we could memory map boot ROM, say at the low side, and have the memory start, you know, above the boot ROM, or we could have actually separate buses. It's kind of in flux. There's advantages and disadvantages to both, but if you made them separate, you could literally grab something from the boot ROM while you're storing something in RAM at the same time. Don't know if that'd be a benefit, but if you kept them separate, you could do that. So this is an example of we're creating stacks in here. Everything's pretty much one line. So logic, you know, just basically means that it's a 1-bit flag, unless you do like that right here. This means 7 down to 0 means this 8-bit register. So here's the boot ROM. This is working. So the boot ROM 0 got an execute, and then a literal. So the literal opcode says, okay, the next thing is going to be a literal you put on the stack, right? Emit, so that's going to emit it out the serial port. We do have to, right now we're using branch and O branch, like in typical fourth microprocessors. I'd like to make that if else and then to be more readable, but you know, it's obviously easier to do it this way when you're doing, you know, kind of bare metal stuff. So that's the entire boot ROM right there. That's a program. It flashes an LED. It emits something to the serial port. So you could write programs, like you could, like say a colon definition, you could put it in here, and you could call this with an exit at the end, right? And you could call it from other words, which are all words or opcodes, unless they're defined afterwards, right? And they're in memory. So here's the outer interpreter. So this is new stuff. Dimitri's been working on this. Like I say, it's working only on a character basis right now, but you can see that even if you haven't programmed the system verilog, it's pretty easy to read. It's very it's an algorithmic level. Can't talk, but so you can see how it's getting it's receiving a character from the UART here. It's looking up in the dictionary. So there's very little code there. Here is a number. It wants to convert the number in here. Very easy code to read, right? And here you is the execute part of it. So this is a work in progress. It does function using a single character. We have to broaden it out to strings. So you can see that was not very many lines of code. So in a task is like a procedure, you know, in like Pascal. So in system verilog. So this is a callable function. And so this is T execute opcode. So this is how you execute something. So here's a task called reset. So you can build all these tasks, and then in your system verilog code down below, you just use the T reset. Done. It resets the computer. It makes the final code extremely readable. So this is the opcode decoder right here. So remember we defined these opcodes up using enum. So case of the opcode is that enum. It's going to decrement the stack, and it's going to the top of the stack, which is pointed at DP. It's going to take the top of the stack and then the second item, and it's going to minus them right here, right? So you can see how we created the minus fourth word in one line of system verilog. So there's plus. See, there's a plus sign instead. So you can see how very easy and readable it is. So you could add your own opcode so easily. And the cool thing about this is all executes in silicon. It executes at the speed of silicon, which is up to 200 megahertz on a typical FPGA. Here's an IO LED where I was doing some testing. So there's an RGB LED. So there's 3 data lines that control it. See how real easy code, right? You don't have to be a verilog guy to understand what that's doing. This is how lit works, and O branch. This is how O branch works. Okay, here's emit. So emit is talking to the UART, right? So this is the UART code. Not much code there. But you can, even if you're not a verilog programmer, especially if you're a C programmer, this looks really familiar to you because verilog was modeled after C. And here's execute. You see we have a busy flag. And that's important because then an opcode can take multiple clock cycles, which we want to, that's why I say CISC over RISC. RISC is the fourth engine. But CISC, you know, we want to just stall execution until we finish that. So we can create a really complex opcode, you know, that could be, it could be 100 cycles. I think typically it's going to be, you know, 3 to 10 cycles, something like that for most opcodes. I don't know what it'd be I don't know why you need it too much more than that. So this is basically the whole engine. And so the always statement in in an FPGA means that's an actual circuit that's created doing this stuff. So if reset, which means external reset, we call T reset. Remember, we defined a task called T reset, so we just call it T fetch. Remember, we defined that task, T fetch. Look how readable that is. This is the fourth engine right here. So this is okay. This is the UART stuff. So this is a bit more complicated, but you don't have to deal with it. We've already coded the UART for you. Look how simple that is. Are there any questions on the code?
Several have been asked in the chat over the last few minutes.
Oh, sorry, I haven't been looking at it. Let me go look. Should I? Oh, okay, there we go. Double cell precision. Let's see. Okay, recursive functions. Double cell precision would take 64 cycles on a 32 bits. So you're talking about a 64-bit arithmetic operation? Oh, division.
I just wanted to provide an example of a useful example for something taking more than 30 cycles.
Yes. So
because a simple shift and subtract division algorithm would run for 64 cycles with double wide arithmetic.
Yeah, FPGAs have multipliers logic built in, so they can do a lot of this stuff really fast. I'm not quite sure what a 64-bit would equate to in an FPGA, but I would expect to be a lot faster than that. But yeah, that's a good example.
I think they don't have hardware division units, only hardware multiplication units.
Yes.
So, but you could probably implement a 4-bit per cycle division or something.
Right. Yeah, so you could write some system verilog that takes 64 cycles and make it an opcode, right? And you wouldn't do something like that. I mean, if you're going to build a microprocessor, they obviously have arithmetic units where they're doing really complicated stuff like that and trying to get it down to a clock cycle or something. So it just shows that you don't have to worry about that. Okay, I don't see any more stuff in the chat. Anybody else have a question?
Yes, I do. And I ask it, why did you state so high numbers for RISC-V cores? There are RISC-V cores like the bit serial SRV core, which fits in a few hundred lots, and even a parallel core like the Pico RV32 fits in about 800 lots or 2000 with all options enabled, which includes optional instructions. So why do you
totally we're not going for speed. We're not going for the smallest fourth processor on the planet. If you want a great processor, go use the J1. Great processor, 16-bit.
Totally different from the system you're describing.
This is totally different. Yeah, we're going more to a CISC engine, but you can implement it on a $2 FPGA.
I think he was asking about the RISC-V core, though.
Yes, the RISC-V core can be boiled down to something like 800 lots and the bit serial one is even smaller.
Okay, yeah, we're using the micro semi RISC-V. For whatever reason, That's the only one that I was familiar with, and it takes 10,000 LUTs on an RTG4 space rated FPGA. And the space rated FPGAs are not are a generation behind current FPGAs, so maybe that's something to do with it. So that was my experience. It's 10,000 LUTs.
You probably you're probably comparing a very big FPGA core against a tiny fourth engine instead of small size optimized cores.
Yeah,
you've probably tried a performance optimized one.
Yeah, so that we're not building a microprocessor, to compete with RISC-V. RISC-V is a micro, right? What does R stand for? Reduced instruction set. So they're primitive instructions, but it runs like a bat out of hell. Well, when you design RISC chips, your goal is to get each opcode, each operation to ideally complete in one cycle. It means you can't do a whole lot of stuff if that's your requirement. Our requirement is we don't, we want to do CISC. If you want to take 12 cycles, take 12 cycles. We want to build a very high level language on top of this when we get done with it. So we're building the foundation. I got to plug my.
It looks like a really interesting vessel for hardware software co-design.
Yeah, I like the idea of having an incremental compiler interpreter decoding my verilog code. This would be great for debugging FPGAs.
Have you looked into it if on the FPGAs you're using it would be possible to load bitcode without stopping the fourth engine running the same FPGA? So partial updates of the bitcode?
Are you talking about the fabric? You mean the
Yes,
configuration?
if you can configure as of yet unused part of the fabric at runtime.
That's a fascinating idea. Don't really see. I mean, it would be great, a great extension to this, but
it would just be a crazy hack.
You would have to sign an NDA, I think, to get the information to be able to do that. But there's an open source synthesizer out there, so maybe there's.
So you're using the official toolchain instead of the open source tools?
Yeah, we're using Radiant from Lattice. We switched from, I was using Libero from Microsemi to start the development. So this code has worked on Microsemi, Libero, Lattice Radiant, and Quartus. So 3 different, it's just high level code that you can pretty much use on any platform. We're trying to keep it very generic that way. You can use it different platforms.
I like to thank Don for his presentation, and I guess move on. If you gentlemen want to continue that discussion, perhaps afternoon or at some later time, either here on this